gather one or two things. Good day, everybody. I had to quickly gather one or two things. We are all welcome to TPATHS Learning Center, and this is a new week, and we are starting a new week with an important subject, which is chemistry. Now, I'm going to be dealing with an important topic in chemistry, and let me not even say chemistry, in jam chemistry, because this is a part in chemistry that we all should expect in the exam. So I'll quickly start it today. Title of it is Energy and Chemical Reaction. Energy and chemical reaction. First of all, what is energy? What is energy? So energy can be defined as the ability to do work or the capacity to do work. Yeah, it's one thing we learned in our basic science back there. So energy can be defined as the capacity to do work, the ability for you to do work. Now you can express energy in various forms, and one of the ways that you can express energy is the kinetic energy. Kinetic energy. There are other ways, like the potential energy, the heat or the thermal energy. We have sound energy, we have light energy. Let's not forget, we have what they call nuclear energy. Nuclear energy. These are forms of energy, and in all, one way or the other, must have used them. You might not even know, but you must have used them one way or the other. Let's continue. And we need to know that energy itself can change from one form to another. The reason why we can easily have the sense that when we take in something, we will gain more energy because we believe that energy can be converted from one form to another. Very important concept. Energy can be converted from one form to another. Now, we need to also understand something, that if energy can be converted from one form to another, therefore, the total amount of energy before and after will remain the same. It will remain the same, and that is known as the law of the conservation of energy. As the law of the conservation of energy, we state that energy can neither be created nor destroyed, but can be changed from one form to another. But can be changed from one form to another. Now, heat content and heat of reaction. Now, we believe that every substance possesses characteristic internal energy, and that is due to the arrangement of the molecules. Now, this is known as the heat content or enthalpy of that substance. The heat content or enthalpy of that substance, because we believe that every substance possesses a characteristic internal energy. Now, if you consider a chemical reaction, heat energy can either be absorbed or evolved. They can be absorbed or evolved. And why can they be absorbed or evolved? Because you look at the reaction like this now. For example, if I have A plus B giving me C, we believe that the energy that this A and B must surmount to get to C will never be the same as the energy required for C in C. So the energy, that is the heat energy involved in this process here, will never be the same as the heat energy here. And that is why we can conclude that heat energy can either be absorbed or evolved. Absorbed or evolved. Now, knowing that, we need to know that if you have a reaction from A plus B given to C, that means the heat energy that accompanies this reaction is known as the heat of reaction. The energy that accompanies this reaction is known as the heat of reaction. Now, you need to understand something, that most of the times, this heat of reaction tends to be constant under certain fixed conditions. Under certain fixed conditions. And I call that fixed condition standard. So we have what they call the standard heat of reaction. The standard heat of reaction, which is the amount of absorbed when a chemical reaction takes place between molar quantities of the substance. Under what? Under standard conditions. The good question is, this is a very popular OBU question. What are these standard conditions? Ladies and gentlemen, what are these standard conditions? Standard conditions includes temperature at 25 degrees Celsius or 298 Kelvin, and pressure at what? 1 meter. when we have this set of conditions, it's called what? Standard conditions. Standard conditions. Standard. It's called standard conditions. When we have this set of reaction, we call what? A standard conditions. So please, let's note this very, very good. So can you understand this? They said heat energy can be measured in what? How can we measure heat energy? The popular one is calories. It can be measured in calories. And what is calories? Calories can be defined as the amount of heat needed to raise the temperature of 1 kilogram of water to at 1 degree Celsius. Now we need to note that fine. One thing we need to also note is the fact that we said earlier on that heat energy can be measured in joules. True. So they can be measured in calories. They can also be measured in what? Joules. And one old unit is known as BTU. It's mostly used in higher industries, in industrial plants. They use what they call BTU. And what is BTU? BTU means what? British Thermal Unit. So British Thermal Unit is a very important thing. It's also a unit too that can be used in measuring heat also. So we are talking about the calories, joules, British Thermal Unit, something new for you to know. And we need to also understand that 1 calories is equal to 4.184 joules. Is equal to 4.184 joules. Is equal to 4.184 joules. That was 1 calorie is equal to 4.184 joules. Now, after knowing that, now we need to also note something again. That we need to also consider the fact that when we have A plus B giving us C, we said earlier on that the heat content of A plus B is not the same as the heat content of C. I want to create 2 scenarios here today. Please follow me. I want to create 2 scenarios here today. So let me show you the first scenario. 2 scenarios today. So please follow me. Please follow me. We are still considering this reaction here. So please follow me. Now we have A plus B given C. What if the heat of A to B is greater than the heat of C, and the heat of A to B, A plus B is less than C? What does this mean? If the heat of A plus B is greater than C, we are tell that the heat of the reactant is greater than the product, or the heat of the product is less than that of the reactant, and that is known as an exothermic reaction. Exothermic reaction. In that case, the heat content of product is less than that of the reactant. Exothermic reaction. But the heat of the reactant is less than that of the product. That is, I'm trying to tell you that the heat content of the product is greater than the heat of the reactant. We believe that more energy must be absorbed for this reaction to form C, and we call that an endothermic reaction. Therefore, an endothermic reaction involves for the heat evolved. It involves heat evolved. While endothermic reaction involves what? Heat absorbed. Heat absorbed. That is 2 things you need to know about. Now, how can we measure the heat of a reaction? We learned that the heat of reaction, we talked about the units, we talked about in terms of the product and the reactant. How can we measure? Can you measure using what they call a part of chemistry called what? Calorimetry. And what is calorimetry? Calorimetry is the science of measuring heat. So the science of measuring heat is called calorimetry, and the device used to measure heat is known as a calorimeter. Now, a calorimeter, we need to know a calorimeter can measure in based on two principles. One, constant volume. Two, constant pressure. Now you can see by the right, we have a bomb calorimeter. A bomb calorimeter measures heat, measures heat in terms of constant volume. In terms of constant volume. Please note that. In terms of constant volume. So we want to do some specific heat of reaction so we can know them. Heat of formation. What mean of heat of formation? We need to have A plus B giving us C, whereby at forming C, we need to know that it is the amount of heat evolved or absorbed when a particular substance is formed. So when a particular substance is formed, the heat involved there is called the heat of formation. Then standard. If it's standard, it is at a standard condition. At a standard condition. Heat of neutralization. What is heat of neutralization? Can be said to be the amount of heat evolved during a neutralizing reaction in which 1 mole of water is formed. That is, heat of neutralization means the amount of heat evolved when 1 mole of an acid, H plus, and 1 mole of a base, OH minus, react together to form 1 mole of water. That reaction, that heat of reaction is called neutralization. Heat of neutralization. It can be in terms of standard, and when it's in terms of standard, then it's called a standard heat of neutralization. In that case, heat of neutralization is at standard conditions. Standard conditions. So we are talking about two things: heat of formation, heat of neutralization, heat of combustion. Heat of combustion can be defined as what? The amount of heat evolved or absorbed when 1 mole of a substance is burnt completely. Please, no star English. Is burnt completely. That is called what? Heat of combustion. Heat of combustion. If it's standard, that is what? At standard conditions. At standard conditions. Heat of solution. All of heat of solution, it is the amount of heat evolved or absorbed when a substance is dissolved in so much water. In that case there, we consider two reactions there: hydration energy and lattice energy. I want to explain that very well for us. So if we have hydration energy, can you see what I said there? I said it is the heat change that occurs when 1 mole of a gaseous substance dissolves in water to give an infinitely dilute solution under standard conditions. So you need to note that hydration energy is an exothermic reaction, and it also depends on the charge density. What is my charge density? For example, now Ni plus Ba2 plus. This is charge density of +1. This is +2. So +2 is better than +1. So you can say that barium 2 plus has a higher charge density than lithium plus. So in that case, we can also say that barium 2 plus will have high hydration energy than lithium plus. So please note that value. That is energy. That energy can be found as the energy released. Please note, it's the energy released when 1 mole of an ionic crystal, is formed from its constituent atoms under standard conditions. That energy, they said that it is always exothermic. The degree of exothermicity is dependent on the charge densities. So don't forget, hydration energy, lattice energy, they both depend on the charge density. So in that case, for example, now, if I have Na plus, plus Cl minus, I'll form NaCl. So in that case, this is called what? Lattice energy. So Na plus in its gaseous state, don't forget, gaseous, before NaCl, what? Solid. So from its this is the constituent atoms to form NaCl. This is called lattice what? Energy. And doing that, you need to go to what they call S law. S law is a very simple knowledge we need to know. What is S law? Sometimes we believe that when we want to go to a specific place, we have various routes or various pathways to go to that place. The major thing there is that the reason we are following various pathways might be due to where you are coming out from, or maybe one is shorter than the other. The major goal of every one of you guys is that you want to reach a specific place. Now what S law is all about. And what is S law? S law states that the enthalpy change for a reaction and it's carried out in a series of steps is equal to the enthalpy change of all individual steps. So all individual steps, the enthalpy, the sum of the enthalpies is the heat of reaction. Is the heat of reaction. Now, you can see there, consider that I have A to B, A to B. Now, A to B, A, D, E to B to C. So this is delta H1, delta H2, delta H4, delta H5, delta H6, delta H3. Now, knowing this here, delta H1 is the real reaction here. So I can say delta H1 is equals to delta H2 plus delta H3. Also, delta H1, you can see that if from A to D, delta H4, D to E, delta H5, E to B. So we are going through this pathway, A, D, E, B, A, D, E, B. But the major thing there that we are getting to our final is so that we can say delta H4 plus delta H5 plus delta H6. That is what S is all about. Maybe next class we'll see how we can pick a question to explain that concept. The last one, Von-Haber cycle. I remember trying to explain lattice energy. And once you need to know about lattice energy, I said it's always exothermic. True. I'm going to be showing you, telling you guys once about, like I measure, you can determine lattice energy of an ionic crystal using Von-Haber cycle. But what is Von-Haber cycle? It is an energy cycle that gives details of all the enthalpy changes associated with a given chemical reaction. The information obtainable from the cycle can be used to calculate the value of an unknown enthalpy change. In this case here, is the lattice energy. So this is achieved by forming a simple equation using the knowledge of S law. This states that the heat change in a chemical reaction is constant and is independent of the route taken by the reaction. That means, I'm going to tell you all today that you can use Von-Haber cycle to determine the lattice energy of the molecule. So I'm going to be showing you a method. I'm going to just use a molecule here as an example. Please follow me and see how we can achieve such value of enthalpy. Let's say I have K solid plus F solid gives me KF. This is what you call the reaction itself. But for it to take place, this solid there has to turn to its gaseous state. K plus. And from solid to gaseous state, this is gaseous state. From this, what has happened there? It has given out one electron. That case, it is called delta H ionization energy. Because ionization energy is the amount of energy required for an atom to lose electron in its what? In its gaseous state. You can recall that this is very, very important. So you have to potassium here is a metal. Potassium here is a metal. So it will lose one electron. And when it loses one electron, the enthalpy associated with that is called ionization energy. Fluorine is a non-metal. Non-metals do not lose electron. What do? They gain electron. So fluorine will gain one electron. So we have F minus. And the enthalpy associated with that is called delta H E E. Delta H E E. Now, fine, this has happened. We have K solid, K plus to F minus. Now, this go ahead to form KF. And that is called what? Delta H lattice energy. This is called delta H what? Formation. So you can tell delta H formation, therefore, because the sum of everything here, delta H ionization energy plus delta H electron affinity plus delta H lattice energy. Plus delta H lattice energy. I believe this is how it should be done, but I'll see how we can use a question to explain the concept very well in the next class. I don't want to just open our mind towards some things. So next class, we'll bring out values, not all these theoretical concepts here. We'll bring out values to explain this concept very well. So from here, you guys say that energy will always be negative. I will prove you that in the next class. So please don't miss next class. It's very, very important. So this, you can see, I've used the knowledge of S flow by adding all enthalpies involved here to get to see, by adding them together to get the data information. So, ladies and gentlemen, we will stop here today for energy and chemical reactions. I want to quickly quote something. Most of the times, I want to quickly, let's note some things before we end the class. Let's note some things. Another thing we need to note is that you need to know that the law of conservation of energy that I said earlier on is mostly known as the first law of thermodynamics. The law of thermodynamics, first law of thermodynamics. I want to put your mind towards some things. We have what they call the second law of thermodynamics. And what the second law of thermodynamics is all about? The second law of thermodynamics is all about the law of entropy. I'll talk about that next class, but I want to open our mind towards it. So entropy, very, very important topic in this course, in this topic. What's entropy? Entropy can be defined as the degree of disorderliness of a system. Degree of disorderliness of the system. The reason why we have the solid, we know we have the solid, we have the liquid, we have the gas. We can compare them in terms of their entropy and explain the concept very, very well. We also have solid as what they call the molecules are held in a fixed position. In a fixed position. In gaseous state, the molecules are in a free, they are free to move, roam around. They are free. And in that case, what happens in that case is the fact that if they are free to roam about, we know that there will be an increase in entropy. Because entropy deals with the disorderliness of the system. And this what leads to what they call the second law of thermodynamics. The second law of thermodynamics. And what the second law of thermodynamics states, it states that in an irreversible process, the entropy of the universe will increase. The entropy of the universe will increase. This is not said here. To open your mind to what you can see in the next class, we also take values to explain. We calculate some questions under heat capacity. A lot of things we are going to do in the next class. So I want you guys to please go through this very, very well, understand the concept. Feel free to also ask questions before we start the next class. And we stop here for today. Thanks for your time, guys. Do have a nice day.